In this example, we are going to form a dual problem from a primal problem. And a primal problem is the linear programming problem that is presented to us that needs to be either maximized or minimized. Now recall that a linear programming problem in standard form, I'm just going to write it down up here. A linear programming problem in standard form has three unique characteristics. And that first characteristic is it has an objective function that needs to be maximized. And we recognize the variable p typically for profit, but we recognize it as a variable for an objective function that needs to be maximized. The second characteristic is that all the decision variables, and those are the variables that are in the body of the system here, are all non-negative. And the third characteristic is that the constraints are all less than or equal to. So as we look at this problem here, this is the primal problem. As we look at it here, we want to minimize it, and we recognize the variable c as the objective function that needs to be minimized. C typically means for cost. Over here, the decision variables are non-negative, but right here, the constraints are greater than or equal to. So it seems as though this primal problem here is the inverse of what a maximization problem would be here. Every maximization problem has a dual problem that's a minimization problem, and vice versa. So what we need to do is we're going to take this primal problem, this minimization problem, and turn it into its dual, which would be a maximization problem. So for letter A here, the first thing we'll do is we're going to write out the constraints along with the objective function. So we'll do 2x plus 5y. That's greater than or equal to 12. And then 3x plus 7y. That's greater than or equal to 17. And then we're going to put in the objective function here, and that's going to be 21x plus 50y. And that's going to be equal to c. So now that we have the constraints in the objective functions like this, we're going to go ahead and construct a basic matrix. So we'll put in a bracket. We'll put in 2, 5, and 12. 3, 7, 17, and 21, 50, and 1. And we'll close off the bracket. Now this is not an augmented matrix, and it certainly is not a tableau. It's just a simple basic matrix that we're going to use to transpose so that we can go ahead and create the dual problem. And each row becomes a corresponding column. For example, the first row of the primal problem becomes the first column of the dual problem. So we'll take this row here, and we'll make that the column. 2, 5, and 12. And you can see it becomes this one here. We'll do the same thing for this row here. We have 3, 7, and 17, as you can see. And we'll do it for the final row here. (21, 50, and 1). And we can see it right here. So now we can close off the matrix. So this is the transposed matrix of the simple basic matrix that we made here. Now we can rewrite this as 2x plus 3y. That's going to be less than or equal to 21. 5x plus 7y. It's going to be less than or equal to 50. And this is going to be 12x plus 17y. And that's going to be equal to p. So now that we have this, we're going to write it as a dual up here. So our objective function is p is equal to 12x plus 17y. And that has the constraints 2x plus 3y. That's less than or equal to 21. 5x plus 7y. And that's less than or equal to 50. And then, of course, x is greater than or equal to 0. And y is greater than or equal to 0. So here's the primal problem. We have a minimization here, objective function, with the following constraints. Here's its dual. We now have a maximization problem with the following constraints. So let's try letter B. We'll go ahead and write out the constraints with the objective function. X plus 2y is greater than or equal to 4. 7x plus 6y is greater than or equal to 20. And then 14x plus 20y, that's equal to c. We then take this and write it as a matrix. We'll have 1, 2, 4, 7, 6, and 20, 14, 20, and 1, and then we could close off the matrix. Now this is just a basic, simple, basic matrix. It's not an augmented matrix, and it's not a tableau. It's just a basic matrix that we use in order to transpose, so we can create our dual. And of course, again, the way we transpose is we take the row, the first row becomes the first column. 1, 2, and 4. We then do the next row. Seven, 6, and 20. That becomes the next column. For the final row, we have 14, 20, and 1. And you can see that becomes the final column. We can now close off the matrix. So we have our basic matrix here, and we have the transpose matrix here. We can now write this as x plus 7y. It's less than or equal to 14. 2x plus 6y. It's less than or equal to 20. And then 4x plus 20y. That's going to be equal to p. So then we could write its dual as p is equal to 4x plus 20y. That's the objective function with the constraints x plus 7y, that's less than or equal to 14. 2x plus 6y, that's less than or equal to 20. And then we add in x is greater than or equal to 0, and y is greater than or equal to 0. So again, every primal problem here, they just happen to be minimization problems. That will have a dual that are maximization problems, and of course vice versa. But there we go.